So with this problem right here, you're asking about, what part of it are you asking about? So let me
I was confused as to where to start because I was looking at the other problem and I was thinking like we had to have more than one product.
well, here you're not going to have more than one product because all of these CH3s are equally susceptible to elimination. Right? They're all equivalent. You're really only going to get one product. This is going to be your alpha site, and then here's your leaving group. So if you just take that side and basically if you drew it out like this, right, and use the base, which is the nitrogen, to pull off this hydrogen right here, you'll get your elimination product. Right, so if that base were to come in, what's that there? That base were to come in here like that, what would you get? You get a double bond right here. Right? This is what your product would look like. So, but you wouldn't get more than one because all of those carbons are identical.
Okay, and how'd you know which one was the alpha hydrogen again?
Just find the carbon where your leaving group is, and the carbon next door to it, that's alpha. So the hydrogens on that carbon are going to be alpha hydrogens.
Okay, so it could have been the one on the left too,
It
right?
could have been any one of them because they're all equal.
Okay.
Mm-hmm. All right. Let's go back to the questions that we're working through. And let's work some more of them. Let's work start my video. Let's work 742. Good question right here. Because we talked about all the mechanisms, E1, E2, SN1, SN2. So let's work 742 and see if we can figure out what it's asking us. So it says, consider the following reaction. It says, how would the rate be affected if the concentration of the alkyl halide is doubled? How would the rate be affected if the concentration of sodium cyanide is doubled? First question, what do we need to know about this reaction to answer that question?
What type of reaction it is?
What type of reaction is it? Is it SN1 or is it SN2, right? So let's go through and look at it and see if we can figure that out. So we have a DMSO as our solvent, which is protic or aprotic. Somebody help me out.
Aprotic.
Aprotic, very good. We got an aprotic solvent. We have a secondary substrate. Right, secondary substrate. Pretty good nucleophile. The cyanide nucleophile that looks like this. Let me draw that out. That is Na plus and then C N. Sorry about that. the carbon is negative. It's a good nucleophile. What we also notice is right here. Right, do you see how that bromine is on a wedge and the cyanide over here is on a dash?
Yeah.
Right? So what that's called is, and I'm gonna give you a little crash course in stereochemistry. So that is what we call stereochemistry, right? It's 3D, it deal, when we talk about stereochemistry, we're talking about the 3D orientation. Right, of a molecule. Right? So one of the hallmarks of the SN2 reaction is what we call inversion of stereochemistry. Right? There's a topic that we're not gonna cover it in this class, but we'll cover it in part 2, dealing with chirality and stereochemistry. And one of the things that's notable is that if a reaction, if a SN2 reaction happens at what we call a chiral center, and this carbon right here is what we call a chiral center. Right, it's chiral. If a SN2 reaction happens at a chiral center, then it's going to get inverted. Right, it's going to go from whatever configuration it is, it's going to be the opposite in the product. So you can see how that's on a wedge, which means it's coming out of the paper or out of the screen. And then on the dash, that means it's going back into the screen. So that's the reverse of what you see there. All right. It's still chiral, but it's just the reverse. So remember when we talked about the SN2 reaction, and we said that, let me go back up, and I'm gonna come back to that. We talked about SN2 first. Let me scroll up to that. Sorry for all the scrolling. Talked about quite a bit though, but this is why I want to go right here. So remember when we talked about the transition state, and we talked about how it's concerted and how the nucleophile is coming in and the leaving group is leaving at the same time, right? So the nucleophile, as it's coming in, right, it's coming in from the opposite side of where the leaving group is. So that's why you see that inversion, because when the nucleophile comes in, it's coming from the opposite direction of where your leaving group is facing, right? So if that leaving group is, and let me show you down here. I'm gonna just cut out this problem and what we have written about it so far on the page, so we can discuss it more fully. All right, so without getting into like the chair confirmation and all that stuff, because we haven't talked about that yet. I'm just going to show this from a 2D perspective. So if this is my carbon right here, and this is bromine, and I have 2 carbons attached to that, and a hydrogen. So put the hydrogen up here. And then the 2 carbons in the ring, I'm just gonna put down there. Right? Sure. Come on, Russell, get it together. So that's bromine, it's on the ring, that's the configuration, right? It's on a wedge. And then the cyanide is gonna come in from this side, like that, boom. It'll never attack from the same side of where your leaving group is. Right, so when that happens, you end up with this. This is C, and then this is H. And now the CN is back here. So let me keep the H point. And this is just a rough, like a 2D sketch, because in order for me to show it to you in 3D, then we'll have to talk about like the chair conformation for 6-member rings, and we're not at that point yet. All right, so that's the cyanide attacking from the opposite side, and then of course the leaving group is left. So let's put it over here. So for SN2, so your nucleophile always attacks opposite of a leaving group. All right, always. So for SN2, this is one of the ways to pick it out. One of your characteristics is inversion. It was in one of those videos I sent to you. But the inversion of stereochemistry gives this away. So the fact that it's inverted tells us that this is an SN2 reaction. All right. So how do we answer those questions? What's the rate law for the SN2? What does that look like?
K, substrate, and nucleophile.
Okay, good. So rate equals K times the concentration of substrate and the concentration of the nucleophile, right? So the question asks, how would the rate be affected if the alkyl halide, which is the substrate, right, is double? So let's just do a little simple math, very simple math. So rate is K times 2 times 1. What's going to happen to that rate? If I double the concentration of the substrate, what should happen to the rate?
It should double as well.
It should also double. All right. All right, I didn't grab B. I don't know how I left that out, but I'll grab it now.
I have a question.
Go ahead.
So when you say that the nucleophile will always attack on the opposite side, like when you first see this equation, it doesn't look that way. So should we just always redraw it?
Say that again now.
When you say that the nucleophile like will always attack on the opposite side of the leaving group, like if you go
Yes.
up to where like it's originally drawn, it doesn't like I guess look that way. So should we always like redraw it?
Well, okay, so The inversion, the opposite side part is always true. The inversion part is not always the case because you don't always have a chiral center as your reactive site. Right, so the inversion part is only important if the leaving group is attached to a chiral center, right? Like we have here. Is that what you're asking? So, but the nucleophile coming in from the opposite side of where your leaving group is, that's always the case. But every substrate is not going to be chiral, right? So you're not always going to see the image of inversion because the chirality may not be displayed. But in this case, since we see it, then we have to take that into account.
Okay, so I was asking, so should we always, I guess, like, because the nucleophile is like right next to the leaving group, like in the beginning. So should we always, I guess, draw it to show that it always on the opposite side?
Hold up, your mic is low, like really low. So you said the nucleophile is
like in the beginning, like it seems like the nucleophile is like right next to the leaving group. So should we always draw it to where it shows that it's like opposite, if that makes sense?
No. That part is just drawing it on paper like that, writing it out. That's symmetrical.
Okay.
Yeah, the place where that matters is in the transition state. So you're saying like the way I have it written, the nucleophile leaving group are on the same side. Is that the
Yeah, in the original.
yeah, so
Yeah.
that's just symmetrical. I could have written that on the other side as well. It wouldn't matter. When it matters is if you are drawing out like the transition state.
Okay.
But if you're just writing the reaction out, A plus B, and B is the nucleophile, and it just happens to be on the right side of A, where the leaving group is facing it, that doesn't change anything.
Okay, but just know it's always on the opposite.
Yes.
Okay.
Yes. Yeah, that's it. So the part about it always attacking the opposite side is always true, regardless of how it's written. When the reaction starts happening, the nucleophile is going to attack the carbon where your leaving group is, your reactive site is going to attack it from wherever the leaving group is. The nucleophile is coming around through the back door.
Thank you.
Yeah, good question. Good question. All right. What about question B? What if I double the rate of my nucleophile? What will happen?
The rate will be double.
It's going to double again. Okay, times 1. We had the nucleophile over here. So 2. All right, so the rate will double. Are y'all following that? This is just an application of what we talked about with the rate law. So any change in nucleophile or substrate is going to cause a change in the concentration of the nucleophile or the substrate. Is going to cause a change in the rate. What if I triple them both? What's going to happen to the rate?
It'll increase by 9.
Yes, it'll be a 9-fold increase, right? What if I double them both? What's going to happen to the rate?
It's gonna be fourfold.
A 4-time increase, a 4-fold increase, yes. Right, so any changes I make to the concentration of either the nucleophile or the substrate will change the rate. It's going to change the rate. All right, is that making sense? Anybody got questions about that? All right, let's do the next question. Let me go ahead and cut it. squeeze all that information in. All right, let's do this question. What do we need to know in order to answer the questions? Look at what it's asking. It's asking about the rate. So in order to know what the rate law is, we need to know what
Type of reaction.
type of reaction we're dealing with. All right. So let's go through and look at some of the clues. Right. We have a tertiary carbon, tertiary substrate. All right. HBr is protic. All right. The tertiary substrate gives it away immediately because and then we have a product that's a substitution product and not an elimination product, right? So that's another clue. If that was an elimination product, then we would have to think about E1. But the fact that we have a substitution product, that tells us that it's a substitution. But now we just need to figure out which one it is. So if we're on a tertiary carbon, SN2 cannot happen at a tertiary site because it's too crowded. Just for the same reason we talked about above, about how the nucleophile attacks. If it's a tertiary site, let me just show you. So if I have a tertiary site like this with a leaving group, right? And I'm trying to attack that back side of that carbon, that's not going to happen, right? This is too, what we call sterically hindered. So tertiary carbons are too sterically hindered. To do SN2, right? So it can't be that. It has to be SN1, right? It's too crowded. The backside of that carbon is too crowded for a nucleophile to attack. So why would the SN1 be more suitable? What is it about the SN1 that happens first that the nucleophile, that wouldn't preclude the nucleophile from attacking that carbon?
The
The
leaving
leaving group leaves.
Leaves first. It's almost like, this is a horrible example, but I've been using it for a lot of years, so I'll keep using it. Somebody got mad at me one time about it, but it's okay. So the SN2 is, don't hate me for this, but there's a old song, a blues song by ZZ Hill. It's called Cheating in the Next Room. So with the SN2, the new person is not coming from the front door. They're coming through the back door, while the current person is leaving out the front door. With SN1, it's different, right? The breakup has already happened, right? So in this particular case, let's go through it and let me show you what I'm talking about. So in this particular case, this is my, I'm just gonna write over here. This is my alcohol. Water on my screen. All right, so this is my alcohol. Sorry about that. I think I got some water on the screen. And this is HBr. This is going to attack here. You're going to lose the bromine. So you end up with the hydronium. Hydronium ion, which leaves, right? We talked about that already. You lose your leaving group. I think I heard you say that, Eli. And then the bromine can come in and attack it. Right? So you end up with, and this was tertiary, I need to add that carbon back in. That's coming there like that, and then you end up with this product. But you see the difference, right? The leaving group is already leaving, so there's no need for bromine to sneak around the other opposite direction. It can come through the front door because the significant other has already departed. They broke up, right? So there's no need for it to come through and try to creep around the backside when it can just come right here, right? And I know it's a horrible example, but it works. I still have students talking about that song too. You can Google it, listen to it later. So yeah, so with this SN1, with the leaving group leaving first, and then the nucleophile attacking, right? What does that mean for the rate? Right? Only the substrate is involved in the rate determining step, not the nucleophile. Because the rate determining step is the loss of leaving group. Is that right?
Yes.
Mm-hmm. So let's answer those questions. How will the rate be affected if the concentration of alcohol is doubled? So we're gonna double the concentration of the substrate.
The rate will be doubled.
Yes. Right, so it should double. All right. How would the rate be affected if the concentration of HBr is doubled? Is HBr involved in that rate law?
No, it's not affected.
No change, right? All right, so hopefully you're seeing the connection between all these different things we talked about. Now that it's time to put them into practice, right? So the rate wouldn't change. Any questions about that, about those two problems that we just looked at? All right, let's answer 744 right quick. DMF, DMSO, and ammonia, protic or aprotic?
Aprotic.
All of them are aprotic. I know it's tempting to think that ammonia is protic because it has hydrogens on it, but those protons, those hydrogens that are on ammonia, the pKa is somewhere between 35 and 45, so they don't come off readily. They have to be pulled off by a very, very strong base. And then ethanol and water are both protic, meaning they can give up H plus. So protic solvent donates H plus. An aprotic solvent cannot donate H plus. Right, let's go to the next section. How much time? 13 minutes. All right, we got 6 problems. How many people we got logged in? 26 people logged in. We're missing like 10 people. That's all right. I'm gonna make 6 breakout rooms. And I'm gonna give you 5 minutes to work one of these problems. I'll assign the problems. Go ahead and screenshot it if you don't have the handout. And I'm gonna make the breakout rooms and I'm gonna assign one problem to each breakout room. 5 minutes, and then we'll spend the last 5 minutes of class for each group giving their results. So let me do that right quick. 6 breakouts. All right. So if you're in room 1, then you're gonna do A. If you're in room 2, B, 3, C, so on and so forth. So go ahead and join, and then I'll send a message. And then, let me just. And you'll have 5 minutes to finish that problem. You really won't need that much time, but. All right, go ahead and join your breakout room because the clock is ticking.